So in the last session, we learned how to draw the transistor level schematic, that is TLS, from the given Boolean expression. So I will not repeat all the rules which we have framed, but ultimately after applying those rules, when we converted the given Boolean expression into transistor level schematic, then by applying all possible combinations of the input variables A and B, we could actually justify that this first circuit actually acts as a NAND gate. Similarly, the second circuit acts as a NOR gate. This is very clear now. So what I will do, I will write the names. So I can say this is a CMOS NAND gate. Similarly, this is a CMOS NOR gate. Okay, so if we carefully observe here, in case of CMOS NAND gate, in the pull-up logic, MOSFETs are in parallel. Okay, so we can write a summary here that for a CMOS NAND gate, pull-up network all MOSFETs are in parallel, and pull down network all MOSFETs in series. And for NOR gate, I can similarly write down that pull-up network all MOSFETs in series, and pull down network all MOSFETs in parallel. Okay, so please understand that the logic gates in whose implementation in pull-up network or in pull-down network, all the MOSFETs are only connected in one common way. So we can say that MOSFETs can be connected in series or they can be connected in parallel. So they are called as simple gates. Okay, so we can actually define simple gates now. We can say simple gates are defined as those logic gates in whose CMOS implementation MOSFETs, all MOSFETs are connected in only one way in pull-up network or pull-down network. Okay, so simple gates are defined as those logic gates in whose CMOS implementation all MOSFETs are connected in only one way in pull-up network or pull-down network. So when I say this thing, I actually say that you can say all PMOS or NMOS in series or all PMOS or NMOS in parallel. Okay, in pull-up network or pull-down network respectively. Okay, so that is why, taking this definition as a reference, we can also define compound gates as compound gates are defined as those logic gates in whose CMOS implementation the MOSFETs are connected in both ways. That is the definition of compound gates. So we can also give an example of that. Compound gates are those logic gates in whose CMOS implementation MOSFETs are connected in both ways, that is series and parallel, in each of pull-up network and pull-down network. Okay, so compound gates are those logic gates in whose CMOS implementation MOSFETs are connected in both ways, that is series and parallel, in each of pull-up network and pull-down network respectively. Okay, so now we can take some sample expressions wherein this definition of compound gates can be appreciated. Okay, so now we take a numerical. Derive the CMOS logic implementation to realize the following Boolean function. So the function given is y is equal to a ANDed with b OR with c whole bar. Okay, so the given expression is a ANDed with b OR with c whole bar. Okay, so let, for example, this is equation number 1. So we can actually first demorganize the expression in this way. You can say given y is equal to a ANDed with b OR with c whole bar, according to De Morgan's theorem, will now become equal to a bar OR with b OR with c whole bar, which can now be written as a bar OR with b bar ANDed with c bar. So now, using De Morgan's theorem, I have converted my parent expression into this. Okay, So we can say we are actually demorganizing the expression. Okay, so now the given expression y, it already has a bar over the Boolean expression. So we can consider y and we can implement the pull-up network before. And now because of applying De Morgan's theorem, my given expression is now a logical combination between complemented variables, which is the best possible expression available to us for implementation using p-channel MOSFETs. So as our previous procedure, what I do is this. So P1 will generate A bar, P2 will generate B bar, and P3 will generate C bar. That means I need 3 MOSFETs. So I can write down like this. I can say P1, P2, and P3. Okay, so if you feel that it is taking too much of space, you can say P1 will generate A bar, P2 will generate B bar, P3. Okay, so I can say here like this, that A is applied to the first PMOS, B is applied to the second PMOS, and C is applied to third PMOS. Now that we have 3 variables, so I need 3 MOSFETs, and see how I converted. This ORing will actually mean now that I have to perform parallel connection here. Okay, so I can also do like this. So I'll say P1 parallel, P2 series P3. Okay, so I repeat here. So the given expression using De Morgan's theorem is now simplified to A bar odd with ANDing between B bar and C bar. So P1 generates A bar, P2 generates B bar, P3 generates C bar. Now I have put B bar ANDed with C bar in a bracket. So between A bar and the bracket I have ORing, that means it is parallel, and then within the bracket I have ANDing between B bar and C bar. It is a series between P2 and P3. So I can actually read it like this. So the pull-up network will consist of the PMOS P1 connected in parallel with a series combination between 2 p-channel MOSFETs. So now this is my pull-up network. So I can actually write it like this. This is my pull-up network, and the pull-down network will now be a mirror image of the pull-up network. So how to write the pull-down network? Very simple. Is that P1 becomes N1, P2 becomes N2, and P3 becomes N3. But you should always take care that here my parallel connection now becomes series connection, and here understand one thing, that P2 series P3 now becomes N2 parallel with N3. Okay, so this is my pull down network. So now after the pull up network and pull down networks have been devised, I have to actually draw them now. So P1 parallel P2 series P3. Okay. So first draw the power rails. Right. Now P1 parallel P2 series P3. So how we should make it now? See carefully how I'm doing it. So P2 is in series with P3, and this series combination is in parallel with P1. So see here. So first I will draw P1. It is in parallel with P2 series P3. P2 series P3. P1 in parallel with P2 series P3. Okay, and because it is PMOS, we'll show bubbles. Okay, and from here it will become my output Y. So this is my pull-up network. And here I'll be applying the variables as I told you that A will be applied to P1. So A, B and C. So N1 series, N2 parallel N3. So N1 is in series. So it will become N1 in series with N2 parallel N3. So N2 parallel N3. N1 in series with N2 parallel N3. And then you can make the connections here. Whatever is applied to P1, that is A, also is also applied to N1. Whatever is applied to P2 should be applied to N2, or else if you want this is becoming too complex or cumbersome or not neat, then you can actually show like this B, you can show C. Okay, so you will appreciate that why I have to write A, B and C here. When we learn the tool microwind, at that time in order to make layouts for simple gates and compound gates, you had actually learn like this. Okay, so if I want to convert this particular CMOS logic implementation into microwind, what I have to do is that I have to actually draw the terminals. So always you should remember that if I tell you to draw the terminals here, then understand one thing, upper of PMOS is always source. Upper of NMOS is always drain. Source, drain, source and gate. Okay. Similarly here, source, source, drain, source, drain, 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 source, drain, source, drain, source, gate, 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 gate. Okay, so we see here that in pull-up network I have both series and parallel connection, and pull-down network I have both parallel and series connection. This is a classic example of compound gate. Okay, so is it clear? Yes. So now I will write an expression and you will tell me that it will lead to a simple gate or a compound gate. Sir, lecture चल recording चल रहा है. CMOS logic implementation of the function y equal to can you tell me that this particular implementation qualifies to be called as a simple gate or a compound gate. Y is equal to AB odd with CD whole bar. Yes. So it is equal to okay. So we have P1, P2, P3, P4. Okay. ORing is there. So P1 parallel P2, ANDing is there, series, and again ORing is there. Okay. So this becomes my pull-up network. Okay. And then my pull down will now become N1 series N2 parallel N3 series N4. Okay, you see here series has been converted into parallel. Parallel has got converted into series connection. Again, parallel has got converted into series connection. So this becomes my pull down network. Okay, fine. So it will be very simple now. P1 parallel P2 series with P3 parallel P4. So again, P1 parallel P2. P1 parallel P2 in series with P3 parallel P4. So this will be my pull-up network. P1 parallel P2 in series with P3 parallel P4. CMOS A, B, C and D, and the pull down network will be N1 series N2 parallel with N3 series N4. So N1 series N2. So for the parallel branch we have this N1 series N2. So N1 series N2 in parallel with N3 series N4. Okay, so now one point I wanted to make is that if this is the CMOS implementation of 2-input NAND gate, then can you tell me if I want to make the CMOS implementation of 3-input NAND gate, what are the changes I need to make in this particular schematic? I repeat, if this is the transistor level schematic of CMOS NAND gate, 2 input. If I want to draw for 3 input NAND gate, then what should be the changes here?
Sir, one more PMOS in parallel in the pull-up network
Correct.
and
Very
NMOS
good.
in series.
Wonderful. So if I add one more PMOS in parallel to P1 and P2, and I add one NMOS in series with N1 and N2, that will become a 3 input NAND gate. If I want to implement a 5 input NAND gate, it is P1 parallel P2 parallel P3 parallel P4 parallel P5 in pull up network, and in pull down network N1 series N2 series N3 series N4 series N5. Similarly, if I want to implement a 5 input CMOS NOR gate, it will be P1 series P2 series P3 series P4 series P5 in pull up network, and N1 parallel N2 parallel N3 parallel N4 parallel N5 in pull down network. Okay, so we see clearly here that the arrangement of PMOSes and NMOSes for NAND and NOR are exactly opposite to each other. Now I will again come to this point when I teach the topic that calculating the area on chip, and we will prove. So I make a statement here that in second year, if a student is asked a question that implement the given logic function using universal gates, then one student will tell that I will implement this function using NAND gates, and second one, because he is the competitor of the first one, he always wants to do which he has not done. Or other side, the second student always wants to do something different than the first one. So first student has told I will implement the function using NAND gate, and the second one says that I will implement using NOR gate. Now, if we see, both of them will achieve the same functionality because NAND and NOR are universal gates. So whatever you can implement using NAND gate, you can implement using NOR gate also. So for a second year student, NAND and NOR are same. I repeat that NAND gate is same as NOR gate because both of them are universal and both of them can do the same work. But when it comes to the field of VLSI, at that time, if you go and ask a VLSI engineer that given this Boolean function, implement using universal gate of your choice, the VLSI engineer will never ever choose NOR gate. He will always choose a NAND gate. That is why we see even in the unit PLDs, we told that older generation FPGAs logic complexity was defined in terms of number of equivalent 2 input NAND gates, not NOR gates. So when we said that this device is XC3S50, so that 50 actually meant 50,000 equivalent 2 input NAND gates. So why Xilinx did not define the logic density of its PLD in terms of NOR gates? Why as NAND gates? Although functionally NAND and NOR gates are same, still VLSI engineer always defines systems or always will choose NAND gate over NOR gate, because when I fabricate a NAND gate on silicon wafer, it occupies 33% less area than NOR gate. That means if I if I have fabricated 2 input NAND gate on a silicon wafer and the area occupied by 2 input NAND gate is X unit square, then NOR gate will occupy an area which is 1.33 x unit square. It will always occupy 33% more area. That is what we are going to prove in this chapter, that when I say why is NAND gate preferred over NOR gate by VLS engineer, because NAND gate occupies 33% less area on chip while offering us the same functionality. So when we come to the topic of how to calculate area on chip, it will be preceded by what is called as transistor sizing of MOSFETs. So when these two topics are covered, we will actually mathematically prove that NAND gate occupies 33% less area than an OR gate, and then when you go on increasing the number of inputs, say 3 input, 4 input, 5 input, the percentage area saving goes on escalating from 33% to almost 88%. So if you implement any functionality using 5 input NAND gate over 5 input NOR gate, you will be saving 87% area on the chip. That is why from VLSI viewpoint, from fabrication viewpoint, NAND gate is superior to a NOR gate, although both of them are universal gates. Okay, that is why I now write a comment here that similarly to implement n input NAND gate, connect n PMOS devices in parallel and connect n NMOS devices in series in pull down network. Similarly, we write a statement here. Okay. So now we have learned how to implement a NAND gate and NOR gate using CMOS logic. Now we should go and learn how to implement AND and OR gates. So it is not that simple. This is why it is. So first we'll use the conventional rules which we have framed in the last 2 to 3 sessions. We will apply those conventional rules for CMOS logic implementation using MOSFETs, and we will see how many MOSFETs we require. That is, we will find a transistor count, and we will see that if for implementing a mere 2 input AND gate, if so many MOSFETs are required, is there an alternative way, alternative approach, so I can reduce the transistor count. So first we'll use a conventional approach. So derive the CMOS logic implementation for 2 input AND gate. So what we do always is this, is that first and foremost we will write the Boolean expression for an AND gate. Okay, so y is equal to a ANDed with b, and you know that our rules say that whether I should implement y or y bar will depend upon if or whether in the expression for y the bar is there or not. I repeat, our one of the rules for CMOS logic implementation is that if our given expression y contains a bar over the expression, then we design the pull-up network first. And if the given expression for y does not contain a bar over the expression, we start with pull-down network. Okay, so that is why I'll write here, since the expression for y does not contain a bar, we must implement y bar. This is the rule. Okay, so since the expression for y does not contain a bar, we must implement y bar, and we know that y bar is implemented always by pull down network, that is n channel MOSFETs. The second rule is y bar is always realized by pull down network, that is NMOS devices. Okay, fine, all other rules remain the same. So what I do is that I will name this equation as 1, and I will say y bar is equal to a dot b whole bar. So now using De Morgan's theorem, it is a bar ORed with b bar. Rest approach remains the same, but always remember this thing, that we have to realize this using pull down network or NMOSes, right? So if my expression was y is equal to a dot b whole bar, expression after De Morgan's theorem would still be a bar ORed with b bar, and here there we have implemented it using PMOS. But here understand one thing, that here RHS is same as before, but LHS is different. You remember this thing? So when we implemented an AND gate, LHS was having y equal to a dot b whole bar, but here LHS is having y bar. What the point? So I will try to make a comment that if my expression was y equal to a dot b whole bar, then please understand one thing, that here the expression would still be a bar ORed with b bar, but this has to be implemented using PMOS. Why? Because we are implementing y, and y actually means pull-up network. Remember this thing. So here understand, because it is y bar, I have to implement using pull down network. That is why what I have to write here is like this. I will say NMOS N1, NMOS N2, and here it is parallel. And one more thing important, that we want to achieve a bar from NMOS. Remember, we want to achieve a bar from NMOS and b bar from NMOS, and you know that NMOS does not complement the input. That means I have to apply a bar to my first NMOS and b bar to first NMOS. What the point? That is why understand one thing, that my pull down network is now N1 parallel N2, and similarly my pull up network will now be P1 series P2. This will be my pull up network. So you see here, because the expression given for AND gate does not contain a bar, I am designing pull down first and taking a mirror image of it to get the pull up network. So now we will start with this. I have to do N1 parallel N2 for pull down. See now how I do it. N1 parallel N2 pull down network. Seems to be simple, but see here. And pull up network P1 series P2. But students, please remember one thing. There is a main difference between this. So as such, if we see this implementation, two PMOSs in series and two NMOSs in parallel. It seems that this is the schematic for a NOR gate, but it is not a NOR gate. It is actually an AND gate. Only difference is here P1, P2. P1 is receiving A here. P1 will receive A bar here. I told you that now we have to apply A bar here. As I told you, I have to apply A bar to N1. This is the difference. A bar and B bar. Okay, and now I'm going to short them. Okay, now students, please understand one thing. A bar and B bar are not available as original signals. What is available is A and B. Just like we say that some gadgets need AC to run and some gadgets need DC to run. So DC is a derived source and AC is the original source. Similarly, when I say that I have to apply A bar and B bar to N1 and N2, A bar and B bar are not available. They have to be derived. That means what? I need to use two NOT gates in order to realize an AND gate here. Okay. So see here now. So I need A bar here, B bar here. So I have to have if I want to convert A to A bar, I need to give it to a NOT gate. And you know that a CMOS NOT gate, it needs CMOS NOT gate needs one PMOS plus one NMOS. Okay. So I need A bar here. I need B bar here. So signal B, signal A, and the output of the inverter is now given to the input of N1. Similarly here So now P1, P2, N1, N2, P3, P4, N3, N4. Okay, so the conclusion is this: if I use a conventional approach, for realizing an AND gate, the transistor count is how much? So it is 4 plus 4, 8. A conventional approach will be like this. Approach number 2. This you know already, right? So this guy will take 4 MOSFETs. Okay, so parallel and series. Okay, so similar approach can be used for even OR gate. So if you implement OR gate using this particular conventional logic, again you will need 8 transistors. If you use the approach that NOR gate followed by NOT gate, again you are going to save 2 MOSFETs. So please understand one thing, implementing logic is good, but along with that, keeping the transistor count minimum is also one of the important requirements. We have 3 more minutes. Anybody has any questions on the discussion done so far? You are free to ask.